Okay, let's start. Okay, so last time we started talking about systems of particles where you have both a single body and a two-body operator, and this is a common problem that we want to solve in many physical examples where you have some particles and the particles are interacting. And today we're going to see how to approach this problem using an approximation. And the approximation is that the interaction is small compared to the single body Hamiltonian, and therefore we can treat it as a perturbation. But to do that, we need to learn a little bit of formalism that will serve us well. So this is the problem, perturbative approach to interactions. Okay, so quite generally, we want to divide the Hamiltonian in two parts, where H naught is a single body Hamiltonian, describes the non-interacting particles, and it's convenient to choose some quantum number lambda that defines it, that actually diagonalizes the single body Hamiltonian. So we write it in this basis as a sum over lambda and epsilon lambda, a lambda dagger, a lambda. Okay, and lambda generally is an index that denotes briefly all the quantum numbers. Sometimes there are more than one, but anyway, it's completely general. And we already know how to solve this problem. What do I mean by solving? For example, we know what is the ground state of this Hamiltonian. Actually, for the case of bosons, it's not so trivial, but actually it is trivial. They all occupy the lowest energy state. For fermions, it's a Fermi C, where all the states below the Fermi level are occupied. And but generally, the ground state is some kind of a Fock state. Okay, it's a state where we have a product over some lambdas, a lambda generally to some power, which allows it to be different from one for bosons. And all of this is applied on the vacuum, and this describes some kind of a Fock state. And there will be some ground state that is of this form. And we also know that the energy of the ground state is going to be something like that. It's just the sum over lambda, epsilon lambda, times n lambda, where n lambda is the occupation of the lambda state. Okay? So this is the single body problem, and now we have some interaction, and the interaction I'm writing in the most general form, but using the basis of these quantum numbers lambda. So quite generally I have to sum over 4 indices, and I have matrix elements. And multiplied by 4 operators, 2 creation and 2 annihilation operators. Okay, so this is the most general form of the interaction, and V with the 4 indices is describing, it's a number, it's a usually a complex number that represents a matrix element of the interaction, and I'm not even writing its definition in terms of wave functions because we don't care, okay? For us, this is the model. And now the problem is that obviously it doesn't look like a pure single Fock state can be a ground state of such a Hamiltonian if I include both terms. So what I want to do is to do perturbation theory on V interaction. And in perturbation theory, what will be the correction to the energy, for example? If the question I ask is, what is the correction to the ground state energy? When I know that the ground state is something of this form, actually let me not call it F because I use the letter F for describing a Fermi C. So this is just the ground state, okay? G naught of the H naught. To calculate the correction to the energy, let's call it E1. This is the first order correction to the energy in perturbation theory. You remember what it is in general? No sum. What is it?
Expectation value of V.
Exactly, it's the expectation value of the perturbation in the ground state of the unperturbed state. Okay, so this is what it is. Okay, let me just put here operators. Okay, so that's the kind of things that we want to calculate, and we see that each term in this, if I plug in this interaction, I get a sum of contributions, and in each of them I have 4 operators. Okay, so I want to be able to calculate expectation values of such operators, and on first sight it looks a bit complicated. So we want to learn some tricks how to do it efficiently, okay, so that you almost know the answer immediately. So, okay, so before we do that, let me define some notations. Yes? Question?
I have one question. In fermions, G naught.
Yeah, for fermions.
And lambda it's equal 1.
Of course, yes.
Okay.
This is general. Okay.
גם לבוזון וגם פרמיונים. לבוזון זה הכל...
No, for fermions, a dagger for the same lambda to power more than 1 is...
לא, זה ברור, לא. כן, ברור לי.
Yes, that's all. Yeah. For bosons it can be anything.
כן, פשוט האכלוס יהיה יותר מאחד שם, למרות שפרמיונים זה פשוט יהיה אכלוס על כל הרמות השונות בצורה הזאת.
Yes, but this is more general. Okay, so I want to introduce some notations. Let me erase this actually, I don't need it now. First of all, this is something I mentioned in a previous lecture, but now we'll learn it properly. I want to define a normal order of an operator. Okay, O here is a general operator. We denote it by two dot column like this, okay? And the definition is as follows. It's let me first say it in words, and then I will show you what I mean. It's if the operator, usually we write it as a product of creation and annihilation operators. So a normal order is when I put all the annihilation operators on the right. Okay? So let me define a general operator of this type. So I can write it as some okay. These are all operators. They are either annihilation, creation, and they can be mixed, and some of them can be products of or powers of creation or annihilation operators. So in a normal order, all the annihilation operators, let me write it like this. So it's all the creation operators are on the left, and all the annihilation operators on the right. Okay? And if you like, actually, there is usually some factor of zeta to the power p, where p is the parity of the permutation that we need to make in order to shuffle all the annihilation operators to the right. Okay, zeta, I remind you, I'm going to use it all the time, is 1 for bosons and -1 for fermions. Okay, so this is what it is, and as a result, you can easily see that if I take the expectation value of this operator in the vacuum, what will I get? If it's normal order, it's 0. Okay?
Why?
Why? Because annihilation operator, because all the annihilation operators are on the right, they act on the vacuum. Actually, as soon as I apply just the first of them on the vacuum, I get 0. Okay, I remind you that a vacuum with respect to a set of operators is defined so that this is 0 for all lambda. Okay?
יש לי משהו קטן שצריך לפרופי. אם האופרטור הזה הוא רק אופרטורי יצירה לצורך, לבין בכלל השמונה...
מרים לי להנחתה. That was the question I wanted to ask you. So suppose, I mean, I defined O to be a very general operator. Suppose it has only creation operators. Then I claim that you still get 0. Why is that?
כי אז מצד שמאלי.
Exactly, right. So notice that we have the following relation. If I take some A lambda acting on the vacuum, and I look at its Hermitian conjugate, what is this? So therefore, because in the expectation value you have both on the right and on the left the vacuum, then any operator, regardless of how many creation and annihilation, the normal order of it gives you zero. It has a zero vacuum expectation value. Okay. Okay. So this is one definition, and now I want to compute another one. Now notice, therefore, that if I can write the operator, the exact operator, not the normal order, as a normal order plus something, I know that the normal order part will always give me a vanishing expectation value. Okay? And remember, our goal is to calculate something like this, and therefore it's convenient to do this separation. So the next thing I want to define is something that is called contraction. Okay. So let me take, I have two operators, A and B. It's defined for arbitrary pair of operators. And it is the following. Let me take A times B minus its normal order. Okay? Okay, so now let's see what it can be. And A and B represent either creation or annihilation operators. There can be two creation, two annihilation, or one like this and one like this. Okay, all the four combinations. Yeah?
אז או קומוטטור במידה וזה הסדר הלא נורמלי.
Okay, so first of all, let me you see that if AB is already normal order, okay, it could be that it's already normal order. Then what do you get for this? Zero. Okay, so it's zero if normal order. And if it's not normal ordered, okay, then what is it?
זה BA קומביין, זה יחס קומוטציה פשוט.
Okay, so if A and B are wait, is that right? Yeah, if A and B are bosons, this is going to be just the commutator, right? Okay, because if they're not normal ordered, I need to switch them. So it's basically AB minus BA. So if they're bosons, this is a commutator. If they are fermions, exactly, right. So if they are fermions, I need to switch them, but switching fermions in order to bring to a normal order requires a minus sign. Okay? And therefore it is nothing but the anti-commutator. So this object, if I'm looking at all the three options, actually there are not really three, there are two, but either for bosons or fermions. What can I say about all the options? In either case, it's a number. It's a number, it's not an operator. So let me denote this number by something like that, like a roof above the thing, okay? And this denotes a contraction. It's named a contraction of A and B, and it actually turns it into a number, okay? And that's again, it's the difference between the actual product operator and its normal order. Okay? Very good. Now, therefore, using this notation, I can just move the normal order to the other side and write the product AB as, which is an operator, as the normal order of AB plus the contractor, which is the number. Now, the normal order AB is still an operator, and this is some constant, some number, okay, which is either 0 or 1, essentially, in most cases, yes?
יש לי שאלה לגבי מה שגרנו פה בנורמל אורדר. הרי כדי לקבל את הנורמל אורדר הזה, אנחנו מלכתחילה לקחנו את האופרטור המקורי, כבר עשינו לו פה את כל ההחלפות, ובגלל זה קיבלנו פה את ה בחזקת P הזו פה. אז למה אנחנו לא מקבלים פה זהותית 0 להכל? כי כאילו זה זהותית, נכון מה שעשינו?
No, so again, if it's already normal ordered, I get 0. If it's not normal ordered, I don't get 0, I get the commutator.
לא, אבל כאילו אינטרס, אז כל המעברים שם.
But after I do it, I get AB minus BA, or plus BA. Okay?
לא, פשוט, זה נתיב.
Okay? All right, so I can always do this. I can write it as normal order, which is an operator plus a number. And if I want to compute the vacuum expectation value of this pair of operator, this product, then what is it going to be?
Only of contraction.
It's only the contraction, exactly. Why? Because the first term will give me 0. Okay, so actually this thing that I called a contraction is the vacuum expectation value of a product of two operators. Okay? And now let's make a little table for actual choices of the A and B, which, as I said, they are just single either creation or annihilation operators. Okay? Yeah, let me erase, and let me erase this. Okay, so I can actually. Okay, so let me first look at two operators. If I look at two quantum numbers, alpha and beta, I have four options. Okay, either A alpha, A beta, A beta, A dagger alpha, A dagger beta, or one dagger, one not, and the other. Okay, there are four options. And what is this? Okay, the contraction of two annihilation operators, it's 0, right? Right? Okay? Okay, so once again, so let me go back to the definition of a contractor. It's the difference between a product of operators and its normal order. If it's already normal ordered, I get 0. This is an example where it's already normal ordered, trivially, right? Because I have only annihilation operators. Similarly, if I have a product of two creation operators, for the reason we said before, this is again the same as its normal order. So both of these give me 0. Right? Okay. Now what about A alpha dagger, A beta? What is it?
Delta alpha beta.
Wait. What is it again? Remember, the contraction is the operator minus the normal order. Now this is also normal order. And therefore this is also 0. So I have only one case. For two operators, I have only one case that doesn't vanish. And this is A alpha, A beta dagger. And what will be the answer?
Delta.
It will be delta alpha beta, exactly. And notice that I don't care if they are bosons or fermions. Okay? For both cases, I get the commutators, and the commutators or anti-commutators are this delta. Okay? So this contractor is actually more general, if you like, than a commutator, which depends on the statistics of the particles. And actually it tells me that, and again, it is also equivalent to the vacuum expectation value of this product of operators. So the result is either 0 or 1, okay, depending on the ordering, and that's the only combination that gives me 1. Yes?
This delta alpha beta can be equal to 1 or minus 1? Or
No, it can be equal to 1 or 0. It's a delta of Kronecker.
Okay.
Okay? Very good. Okay, so that's great. So if we have an operator that is just a product of two operators, we know how to calculate its expectation value, but that's trivial, right? It's trivial. What we really want is eventually to calculate expectation value of something like this that has at least 4 operators or even more. So we need to be able to work with operators that are more general, that are a string of many, if you like, many creation and annihilation operators. And there is a theorem that you can prove. I'm not going to do it, and I'm not sure even that Sarah will get to it in the tutorial, but we'll definitely post the proof on the Moodle, because it's really mathematical. I mean, it's really using induction and all that, but let me just state the final result, okay? Because the final result is extremely, extremely useful. So the theorem is called after a person named Week's theorem. And it is the following. if I'm looking at, I have a general operator that is a string of product of operators. I can, just like what I'm doing now is kind of a generalization of this equation where I split the operator to its normal order plus just a number. For a longer string of operators, what I have is, first of all, the normal order, plus, and this is the part that will give me definitely 0 in the vacuum expectation value. The second term is a sum over all possible single contractions among the many operators, where what I do is I take the string and somewhere I contract to two of its operators, and I'm summing over all the choices to pick a pair and contract it, okay? And after I contract this pair, I turn them into a constant, and I still remain with all the other operators, and I put normal ordering on them. Okay, so this will be the next term, and then I have another term over double contractions of the same idea. So what I'm doing, I'm picking some pair of contractions. I'll give you later examples, but again, what I'm doing, I have a string of, let's say, 6 operators, and I take 2 of them and contract them, and 2 other and contract them, and then I'm left with, in this case, it will be only 2 operators that are not contracted. It will still be an operator, and I normal order it. And then this is a sum that has as many terms as the number of pairs, if you like. What will be the last term is contracting everything. Okay, so it's the sum over all the possible contractions where I contract this and this, this and this, and okay, so everything is contracted, and I get just a number. Okay? Yes?
What is the תרגול of this של הדבר הזה?
What is the what? Sorry?
אורך. כאילו, לכמה...
No, so let me explain what, in a simple example, what I mean by this notation, because so suppose I have just 4 operators, okay? So the terms in this term, I will have something like this, okay, with a normal ordering, so it will be a number times the normal order of the CD. I can contract A and C, and then I get, okay, let me, sorry. I can contract A and C, and then I will be remaining with B and D, but notice that here, in order to contract A and C, I had to reshuffle the C over here, and then I pick a factor of zeta. Okay? And then I have another option to contract A and D, etc. But each time, when I'm doing the contraction, I get a number times a normal order of the other 2 operators. Okay? And in the next term, in this term, I have two contractions. So this will give me AB contractor, CD contractor, plus all the other all the permutations. Okay? Okay, and I emphasize that the second term here, in order to get to it, I first have to apply a switching between C and B, and that's why I pick a zeta. Okay? Okay, so this is what Wick's theorem says, and it's usually some long expansion, but what can we say? What can it tell us about the vacuum expectation value of the general operator? You see that all the terms except the last one will give me 0, right? So in fact, if we are interested in vacuum expectation value, we don't care about all this. We care only about the last term, and we'll write it as follows. So A, B, C, vacuum expectation value is just given by the sum of all contractors of okay, it's a sum of a product of all the pairwise contractors, or let me write it more transparently. It's a sum of pairings of vacuum expectation value of A alpha, B alpha. Okay? So the vacuum expectation value of a long string of operators is a sum over all the possibilities to divide it to pairs. And for each term in this sum, we get a product of contractors. But the contractors are just the vacuum expectation values of pairs of operators. Okay? Now, actually, there is something you should have asked me here. What happens if I have, I told you that I have a long string of operators. I didn't tell you how many there are, and it could be in particular an odd number, right? Here I'm talking about splitting to pairs. But what happens if I have an odd number of operators in the string? Then I don't have to do any calculation. The vacuum expectation value will always be 0. Always. Always. Okay? So first of all, so what I have here is, let me put it in a box, because this is like the most useful identity we're going to use. Okay, and this has meaning, or it gives you something non-trivial, only provided that the operator, this string of operators, has, not only does it have to have an even number of operators, it also needs to have equal number of creation and annihilation. Right? Why? Because the contractor of 2 annihilation or 2 creation is always 0. Okay? So So this is, maybe I should have said it in advance, this is non-zero only for equal number of A dagger A, okay? In other words, only an operator that preserves the number, the total number of particles, does have a finite expectation value. Okay, in the vacuum. Okay? Good? Okay.
אני לא כל כך הבנתי את המעבר לצורה של התהייה.
Which one?
לא
This?
את המעבר, לא
Or this?
השני, כן.
So here I'm summing over all the possible choices of pairings, of dividing the product to pairs. And I put contractors on all of them. And and of course, sorry, I forgot something very, very important. Very important, the zeta to some power. It's very, very important. Okay, so actually this I no longer need. Okay. Okay, so this is zeta to the p. P is just a notation for the parity of the permutation I have to make in order to create this pairing. Okay, and we'll just now see an example, and it will become very transparent. But the idea is that what you have here for each term in the sum, I have a product of contractors, and the contractor is nothing but a vacuum expectation value of a pair of operators. Okay? And I take the product over all alpha. So each pairing is dividing to a set of pairs, and alpha is the index of a pair.
זאת אומרת שהמכפלות שאת לוקחת את כל ה-A, B, C, D, E, F וחלקת אותם פה פעם לזוגות, כל הדבר הזה
זוגות. After I'm finished, I have just a product of contractors, and each contractor is a vacuum expectation value of 2 operators.
אז הקונטרקטורס הם בעצם כוללים זוג של פרטיות?
Yes.
לא יכולים לכלול יותר.
Yes, so right. So this is just, this is a contractor. Okay. The contractor is a vacuum expectation value of a pair of operators. Okay?
ולמה האפס הזה חוזר עצמו, מצבים האלה חוזרים עצמם כל פעם, לצורך העניין?
Which?
כאילו לכל מכפלה פה מבין המכפלות פה יש לה ערך תצפית, ולמה זה?
Right.
אם היה סכום בין כל
I mean, it can be zero, but in some special cases, but usually if the number of creation and annihilation operators is not zero, it will give you something.
עכשיו שפשוט למה אנחנו פה מקבלים את הערכת התצפית של האפס הזה על כל אחד מהקונטרקטוס, על כל אחד מעל A הפעם?
I don't understand what you're saying.
אני אשאל את זה אחר כך.
Okay? Okay? Okay, great. Yeah, I mean, I think maybe I understand what you wanted to ask. So I could put here a 0, 0, but this is a number. Okay, so it's just this number times the 0, 0, which is 1. Okay? But it's also transparently convenient to write it like this. Because, right. Okay? Okay, so good. Okay, so that's general. This is a theorem, Week's theorem, and now we're going to use it for a problem of interacting fermions. And we're going to be able to say something specific about the perturbative treatment of the interaction. Okay, so I think this table I want to keep. So let me just leave it on the side. This is all 0, and A alpha and beta dagger is a delta alpha beta. Okay, this is one thing I want to keep. Okay, and now we are talking about interacting fermions. Okay, so in fact, I want to write the Hamiltonian right here. Let's begin. H naught is the sum of a lambda epsilon lambda, A lambda dagger A lambda, and begin. Erased it, but let me write again. Lambda, lambda prime, V mu, mu prime, lambda, lambda prime, A dagger mu, A mu prime, A lambda prime, A lambda. Okay, the convention I keep all the time the same of the order of indices. And for fermions, we also know that the ground state of H naught is a Fermi C. Namely, it is a product of lambda belongs to the Fermi C, all the occupied states of A dagger lambda acting on the vacuum. And I just remind that the definition of this is that it's epsilon lambda is smaller or equal to the Fermi energy. That's a definition. So it's inside the occupied levels below a Fermi level. Okay? All right. But now the problem we want to solve is to calculate an expectation value of the interaction, not in the vacuum, the real vacuum, if anything can be called real, because the vacuum is also not empty, not really empty. We don't want to compute it in the vacuum. We want to compute it in F. But F, this is something we introduced last week. F can be redefined as the new vacuum for a new set of particles. If we make the following transformation, we define an operator C lambda, and to be either an annihilation operator, and this is if it's let me just check something. So so if it's not inside the Fermi C, it is the annihilation operator A, but if it is, it's a creation operator, okay? And I remind you my definition of this theta. In fact, it can be written as a theta function. You know the theta function, right? So it's a theta of E Fermi minus E lambda. So if E lambda is smaller than E Fermi, it gives you positive, and then it's 1. But if E lambda is bigger, you get 0. Okay? It's the theta function. Okay. The function of x. Okay? Okay, so that's just a shortcut notation for the theta function. So C is either annihilation or creation operator, but the reason that we define it is because we notice that for any lambda, C lambda acting on F gives 0, and therefore it's properly defined as annihilation operator with respect to the new vacuum. And because this vacuum is actually composed of occupied states and empty states, one possibility to create a particle above it is to create a hole. And that's a particle, just like, as legitimate as a particle itself. Okay? So in order to compute the expectation value of the interaction in F, I want to convert into these notations. But let me first just see how we can use the weak theorem to compute an expectation value of just one term in the sum. So notice the V int is a sum over many, many terms. This is just a number, a matrix element. And each term has 4 operators, and notice there are 2 creation and 2 annihilation. So this is something that in principle can have a vacuum expectation value, according to weak theorem, right? But let's see what it gives. So A mu dagger, A mu prime dagger, A lambda prime, A lambda. This expectation value is given by the weak theorem. What do we do in the weak theorem? We look for all the possible pairings of 4 operators, and each of them gives me a product of contractors. Okay? Now, before I write them on the right-hand side, let me use colors. I have 3 colors that I'm allowed to use, I think, for just that it will look good on the recording. So, fortunately, I have only 3 options here, right? So how can I divide these 4 operators to pairs? One option is to do this. Okay. Another option is to do this. Let me write it here, just not to confuse. Okay. And the third option is to pair this with this, and this with this. And notice that when I do it, I have to have a minus sign because these are fermions. Okay? Now let's write them one by one. So the first term will give me a dagger mu prime times a lambda prime, a lambda contractor. Okay?
Zero.
Now actually it is, wait, we have to convince ourselves, we have to be a little careful because of the conversion to C, because remember this is not the vacuum. It still will give us 0, but we'll have to check. So I'm leaving it, for the time being I'm leaving it. Now the second term with the blue, let me use the blue color. Here I contracted this one with this one and this one with this one. I don't have to do any reshuffling, right? So it is a mu dagger, a lambda contractor, a mu prime dagger, a lambda prime contractor. Okay, so and it comes with a plus sign because there's no odd number of reshuffling. The third term is coming with a minus sign, and then I get a mu dagger with a lambda prime contractor and a dagger mu prime, a lambda contractor. And that's it. I'm done. Okay, there are only 3 options. Okay, great. Now let's see what each of them gives. So first of all, as you said before, the first term will give me 0. And why is that? We have to be a little careful. And let us do a calculation on the side, because when I'm writing this, I cannot use these contractors because here they are defined with respect to the vacuum, right? So I have to first convert a general operator to the C's. Okay? So let me let's write it like this. So if I'm looking at the contractor of a lambda prime, a lambda, to annihilation, what is it in terms of the C's? So each of these is 1 minus theta function times C lambda plus the theta function times C dagger. Okay, I can always convert, I can, if I invert this transformation, it will also look the same. Okay, so it will give me 1 minus theta C lambda prime plus theta, sorry, this is lambda prime times C dagger. And this I have to contract with the same thing with the lambda. and I'm contracting this. So if I contract two annihilation, now the C's are really annihilation and creation. So C and C gives me 0. C dagger gives me 0. C dagger C gives me 0. What is the only term that could give me non-zero? It will be putting annihilation here and creation here, right? This is like the last option. So it's 1 minus theta lambda prime f times a theta of lambda f of C lambda prime C lambda dagger contracted, okay? And this is a delta of lambda prime, and therefore it is actually 0. Why? Because it's a product of theta and 1 minus theta. So it's either 0 or 1, and the product always gives me 0. Okay? Is it clear?
למה החלטת פה את זה ישר לסינק?
So I use I want to know what is this, and it's not clear to me because the contractor here is, I want to define it with respect to the new vacuum in terms of which the A's are not clear, okay? They are not going given by this. I have to convert to C, to the C operator.
אוקיי, אבל איך ידעת ש-C באמת תקבל ככה ולקבל בצורה? איך ידעת בעצם שתקבל את זה בחצי שלך?
This is the inverse of this transformation. It's a trivial transformation. Okay? You can easily convince yourself. It's actually, yeah, very simple kind of transformation. Okay, so these two, these are 0. Okay? But now, if I'm looking at the other two terms, so let us now, okay, so first of all, this is 0, and now I want to look at the other two terms, and notice that one of them comes with a plus sign and the other with a minus. What is the difference between them? Why the minus sign? Because we had to exchange two operators. So if you remember last week I talked about direct and exchange term, or the Hartree and the Fock. So these are the two terms, okay? In any interaction term, you have such combinations, and here we're going to see what they give for the vacuum expectation value. Okay, so what is A mu dagger A lambda contractor? Okay, so once again, if the A's and if the A operators were annihilating the vacuum, you would get 0, right? But that's not the vacuum for the A, it's the vacuum for C. Okay? So let's again use the transformation to the C operators in order to see what we get from the contraction. And for the C operators, we are only going to get one term, one combination that will give us non-zero, and that's the one that has C dagger. Okay? So let me write it down. A dagger is 1 minus theta mu C dagger plus theta mu C mu. It's just the conjugate of this transform, the conjugate and the inverse of this transformation. That's for A mu, and for A lambda I get 1 minus theta lambda of a lambda plus theta of a lambda dagger. Okay, and I want to put a contraction on these two. Yes?
איך את יודעת איך להציב, איזה CU להציב במקום A, כאילו, מתי לשים דגר?
Oh, sorry, I made a mistake. Sorry, this is C, of course. It's converting, sorry, I got confused. It's converting from A. I use the inverse of this transformation.
Yes, but how you... את הופכת אותו בעצם.
Why? Yes, but it's going to give the same. You do the calculation, okay? It's really trivial. The A and the C are, yeah.
But in the Hamiltonian, we have A or C.
In the Hamiltonian, as we wrote it, we have A. That's the thing. We have A. But we can write the A in terms of the C. That's why I'm doing some work, okay? But once I finish it, I get a formula, okay? So the Hamiltonian, once again, the problem we have to solve is we have a many-body problem, okay? And the interaction is given in terms of electrons, let's say, if they are electrons, okay? But in order to do a calculation, I need to work with operators that will observe the field Fermi C as a vacuum. And they allow for being either electrons or holes. Okay? That's the idea.
In the definition of C, it says C equal to something of A. But,
right.
But here you take...
I do the inverse transformation.
Yes, it's okay.
Okay? And the inverse transformation, because they're just 1 or 0, the inverse transformation has the same structure.
Okay.
It's actually the same transformation. Okay? Yes?
לגבי החלק שאמרת שאנחנו צריכים להגדיר את זה ביחס ל-F, אבל כשאנחנו נגיד הגדרנו את זה ביחס למצב האפס לפני כן, לא אמרנו שום פעם אחת שאנחנו מגדירים את זה ביחס למצב האפס בנגיד.
Yes, we did.
באיזה שלב?
In the beginning. Okay. Okay. If I'm not telling you otherwise, the vacuum is a vacuum and the A is with respect to this. Each time, we have to be very careful with this. Each time you work with operators, you have to define the vacuum. Okay, the vacuum is not unique. It's a matter of a problem. And later in this course, I hope maybe next week or the week after, we're going to see a non-trivial example where the vacuum is something a bit more exotic than a field Fermi. Okay? But it still can be viewed as a vacuum for some operators. Okay? All right. Great. So you agree. I mean, if I invert this transformation, I get the same splitting for the A in terms of the C, and that's what I'm using. And now, once I do it, I'm in business because in terms of the C's, there is, once again, only one combination that doesn't vanish. What is it? It's the one that has C here and C dagger here. Okay? So therefore, the result is, and notice what I get, it's a theta of mu times a theta of lambda of C mu, C lambda dagger contractor. But this is a delta of mu lambda. A delta of mu lambda. And because of this delta, mu must be equal to lambda, and therefore it's like multiplying a theta by itself So it's either 1 or 0, right? And therefore, let me write the final result. A mu dagger, A lambda contractor is, in fact, just a theta of mu, delta mu lambda. That's all. Very simple. Okay? Okay, and the same thing, so you see that all the contractors I have here are of this type, right? I just have to plug in the correct indices. Okay, and each time it's going to be a different delta. Very good. So now we are in business because I only looked at one term out of many in this expression for the interaction. But the interaction now includes the sum of everything, and each such term is going to be multiplied by the matrix element. Okay? So we now can calculate the final result, which is the expectation value of V interaction inside the Fock state, the Fermi C state F. Okay, so I believe I can erase this and just give you the final result. And I want to emphasize that you have two terms here, okay? Two terms that will contribute. One is direct with a plus sign, the other is with a negative sign. Okay? Okay. Okay, and I also want to keep the definition of the theta, just for good measure. This is a theta function of EF minus epsilon lambda, okay? All right, so V interaction F is going to be the following results. It's a 1/2 sum over all the indices, matrix element, matrix element times, now we are using all these, I'm taking the expectation value of this operator, and I have two terms, one from the direct, one from the exchange, so let me write them down explicitly. The first one will give me a theta, I'm just plugging in the result, theta of mu delta mu prime, mu lambda, sorry, my eraser. Copy from here. Times theta of mu prime delta of mu prime lambda prime, okay, minus theta of mu delta mu lambda prime and theta mu prime delta of mu prime and lambda, okay? And actually the thetas I can take out of the brackets because they are a common factor that gives me, basically, it tells me which indices, which states are occupied. Okay, it's 1 for each mu that is below the Fermi level. And now I can use this delta function to reduce the number of indices, right? And this is what I get in the final result. Write it once again. So it's 1/2. And now I'm summing over, I can write it as sum over only 2 indices, because you see, for both terms, I get rid of the lambdas. And I have the sum over mu and mu prime, but not every mu and mu prime will contribute. Which are the mu and mu prime that will contribute something? Only the ones that where the theta is non-zero, right? So these are all the mu and mu primes that belong to F, that are occupied states. Okay? And that's the definition. And then, okay, let's see what I have from them. So I will get 2 terms. That's all. In one term, I have the matrix element that remains is mu mu prime, mu mu prime, minus v mu mu prime, mu prime, mu. Okay? That's all. I have a summation over matrix elements. This guy, if you look at the notes of last week, what is this? It's a term that has the indices are mu mu prime, mu mu prime. This is what we called direct, okay? We wrote it in terms of indices of a lattice site, but it doesn't matter. It's true for any quantum number. This is direct, or Hartree term. The second one, which comes with a minus sign, is the fork or exchange, because it differs by, we basically switched the other 2 indices. All right? And this is the final result. Now, what I wrote here is the final, basically the result that we computed this way. Of course, we have to know what are the values of these things. And now it depends on the particular problem, and compute the sum. That's all. Okay. And for the example of Coulomb interactions in a metal, for example, we know how to compute it. Okay, I don't know if I'll get to it today, but basically we can, and that's all we need to know. Okay, so that's a formula for any system of interacting fermions and any type of quantum numbers. Okay. So now the approach that we took here was that we did perturbation theory, just standard perturbation theory. We had Hamiltonian H0 that we solved. We worked with its ground state and computed the correction to the energy to first order in the interaction. There is another approach to get the same result, and that's to make the approximation not on the final result, on the expectation value, but on the Hamiltonian itself. Okay, and let me explain what I mean by this. So I'm first writing the most general I can erase this, right?
Yes.
Okay. I first write the most general version. Okay, so I have some Hamiltonian, some interaction Hamiltonian. Let me just write. Which is expressed in terms of okay, and I have some of contributions. Never mind. Okay, actually, let's just look at this one term, and that's an example. Or okay, maybe I'll write it like this. It's a two-body operator that can be written as a sum of all indices. There's some matrix element, blah, blah, blah. Okay. Now, I'm making an approximation. And I'm claiming that I can replace it by a mean field version. Okay, MF stands for mean field. Where the idea is the following. Why is this two-body term complicated? Because it has 4 operators and not 2. It's a two-body. If it was just two-body, if we add a two-body, if we add a one-body correction to any Hamiltonian, we can very easily diagonalize it. Okay, now it becomes a matrix that is non-diagonal, but we can diagonalize it. Okay, so what is the idea about mean field? I replace the two-body operator by an effective one-body. And the way I do it is just like you saw probably for spin systems in statistical physics, in the Ising model, for example. You do mean field. You replace part of the combination of operators by their expectation value. And the expectation value is a number. And therefore, the remaining thing is just single body operator. Okay? So what is going to be the mean field? It's going to be, okay, we have here sum of indices, etc. And what I do now, I take each time I take a pair of operators and replace it by its expectation value. So I get something, just a minute, let me finish and answer the question. So I get something like this, plus A alpha dagger, A delta, A beta, A gamma, minus A alpha dagger, A gamma, A beta dagger, A what is left? Delta. Okay? Yeah. Wanted to ask something?
What means these 3 points? Alpha, beta,
I'm just not, I'm lazy to write the indices.
It's alpha, beta,
It's
gamma.
just the same thing we always have. Okay, it's alpha, beta, gamma, delta, and this is the sum of all of them. It's just to denote the most general two-body.
The sham gam.
Yes, yes, the same thing. Yes, but I don't care. I mean, what I care is, basically what I did here, I replaced these 4 operators by a sum of terms each of which have only two, okay? And the expectation value gives me some number, and this number times, so for example, if I look at, let's look at the first term, the first term, once again, in the most standard case will vanish, right? Because it's A dagger. But if we, for example, look at this term, so I have a term that is a number, the matrix element, multiplied by another number, which is this expectation value. And I then have A beta dagger A gamma. So it's a single body term. Okay? And
we need also an expectation value of A gamma A delta.
We need everything, right? Actually, to do it carefully, you have to take all the combinations. Actually, if they are dummy indices, then you don't need to repeat all the options, but you have a factor of half. And, okay, you have to be careful a little bit with the counting, but if you do it correctly, what have you done? What have we done actually? It's just like with the story of the spins, where it's very intuitive. You have interacting spins like Heisenberg model or Ising, and you know that each of the spins applies a force that is like some effective magnetic field. But it's not really just a magnetic field, it's because it's an operator, it's something that can fluctuate, right? This is in statistical physics because of thermal fluctuations. But if we average over all the neighbors, we get some effective thing that is just a number, just a constant vector, and that acts like a field. And that's why it's called mean field. So this is the generalization of that idea, okay? So it's like the expectation value for the other particle. The other particles apply a force that is proportional to their expectation value, okay? So, so if you do it for the problem of interacting fermions and calculate, so actually not only for fermions, sorry, it's also true for bosons, but the bosons will not have the minus sign, okay? But we are focusing now on fermions. And so the approximation where we replace the true Hamiltonian by its mean field, the mean field version of it is called Hartree-Fock. Why Hartree-Fock? Because it's going to have only two contributions. One is from the direct and the other from the exchange. This is called Hartree and this is called Fock. Okay? And for a standard field Fermi C, this is 0. The first term gives you 0. Okay, so so what is the Hartree-Fock Hamiltonian? Let me write it in the general form. It's going to be, of course, H0 remains the same. We didn't touch it. Okay, that's the term that is already single body, but the interaction will look like this. It's 1/2. I'm using the notations as above. Lambda prime, V mu prime, lambda prime. And then now what we have is, let me write it carefully. So we have A dagger mu A lambda prime minus A mu dagger A lambda prime A mu prime A lambda. Okay. Well, when I'm writing this, okay, when I write just expectation value, I mean it's just a short notation for expectation value in the ground state of the Fermi sea. Okay. Okay, this term is called once again. This term is called R3, and this is the Fock term. And the Fock term is usually more interesting. Why? Because it comes with a minus sign. So it's if you have, for example, a repulsive interaction, it sort of gives you an effective attraction, in a sense. All right? Yeah? Just, again, it's something. Okay, this is a something. Okay? This is just a definition of when I write these angular brackets, what are they? Okay? Good. Okay, and by the way, notice that, I mean, again, here, the mu and lambda are just dummy indices because of the factor of half. I don't have to worry about, I'm not double counting. And next week, we're going to apply it for an example, which is the Coulomb interaction in a metal. Okay?
Okay.
And see what you get. Okay? So thank you for the attention.
שזה בעיני בתחומים, ואחרי שזה לא עובד, יש כל קובלט, זה לא עובד כי נגיד שמתחת הנגד פרמית, אני כבר רוצה יוצא אפס. מעל הנגד פרמית זה יוצא. ואני רוצה לא כל זאת שזה
בסדר, זה כמו שעשינו במקור את הסילם, עשינו עם לשפר ראש. צריך לחלק את זה בכל זאת.
לא, אם אתה רוצה להגיד אפשר לדעת את A, לצורך העניין, C או CPA, אז צריך לחלק את זה מחדש בקורבי. זה לא כל כך באפס, שאתה רוצה.
למה שאתה קונים באפס?
כאילו, תראה, A נגיד צורה שלו, נכון, C שווה משהו מ-A, נכון? יש לך שתי משאבות, כאן C ו-C ו-A. אז אני רוצה לדעת את A ו-A, נכון? לפי C. אני אנסה לחבר משפחות.
אבל אתה לא באמת מבודד, אתה לא מחלק. אתה פשוט רושם ביטוי אחר. כאילו, אם תציל פה פשוט תציל למדה.
Okay, it's 6. Can anyone check if there's still people outside? I don't want anyone to miss anything. Okay. So, you just finished writing the titles. Okay. So, continuing from the last tutorial about application of second quantization, we go for our second example, the Mott-Hubbard transition. If you remember, last time we talked about the free electron gas with interaction, and now we're talking about a different subject. All right. Let's assume that we have a lattice structure. Sorry, I'm gonna turn off my phone. Not okay. Let's assume we have some sort of lattice structure with only two sites. Hold down site 1 and site 2. All right. I'm gonna create 2 copies of them. We'll see why in a second. Second quantization. I will just leave it. All right. So we have a lattice structure with only 2 sides. And in this lattice, we populate this lattice with electrons. These electrons have half a spin, and the only differential quantity between them is their location and the spin. So we know, so in this lattice interaction, we have the possibility of an electron. Let's say an electron position 1 will spin up. We have the possibility of it going to lattice position 2 with some transfer energy T, or we can have I gave someone my other black one. All right, the second interaction will be called on-site interaction. It's still noisy, but fine. Some U, all right? This is a 2 possible interaction. Again, notice that there can only be a double occupation of each lattice space from the Pauli exclusion principle, and we can only put 1 up and 1 down in there. Those are the options. So the Hamiltonian will be divided to the 2 interaction, the T and the U. So we'll write it HT plus HU. Well, HT will describe for us some negative energy interaction, sigma, up, down, so over I, 2, A, I, the dagger sigma, J, sigma, right? Or if we write it explicitly,
It's okay.
all right. So again, we have a Hamiltonian part that describe an electron moving from one side to the other, and then we have the on-site interaction HU equal to U sum over I up and I down, right? Or explicitly U times N1 up N1 down plus 2 up and 2 down. Right, this is our basic Hamiltonian. We know this system can support up to 4 electrons, and specifically we want to find out the cases where we have an isolating material. First of all, if we have full occupation, 2 electrons here, 2 electrons here, there will be no possible transition, so that's one of them. And also if we have 0 electrons, that will be another trivial case where we don't have any conductivity in this material, in this lattice. Now we want to take a specific case where the total number of electrons is 2 and try to explore it, find the isolating states. We'll find that in a certain case we can get a non-trivial Mott isolator, which will be our question. Which will be the final goal for this example. So Let's discuss half filling. Half filling n equals 2, which will equal to n1 plus n2. Okay. And let's write all the possible cases. Just give me some space. Let's
Just
yeah. Just want to write, erase this here. This one for now. Okay. So, how can we put in the two electrons? First of all, we have what we call the spin polarized state. Spin polarized, which will be, we write it as P equals P2. So basically, you put two electrons in the same spin into one lattice, and there's two possibilities in the two different lattice spots, and there's two possibilities: A1 down, A2 down. This will look like so. So it's 1, 2, up, up. This will be P1. And P2. Down. All right. Then we can do the exact same thing. Put one electron in each lattice spot, but in different spins. We call those the S signal occupation. Single occupation. S1 would be P1 up, W times A2 down, dagger is 0, is 2, to be A1 dagger, A1 down dagger, A2 up dagger, which will look like down, down, up. Okay, and the final one will be called double occupancy. So D, call it D, 2, 1 up, dagger 0, T2 equals A2 up, 2 down. Right, this will look like down. Okay. You can check me on this. This is our 6 possible basic Fock states that will span our space, our state space. Right. Now, when we want to solve some quantum systems, the most common thing that we want to do is try to find the eigenstate and the eigenvalues.
Like that's the בעצם הגדרת פה את 3 הסוגים האפשריים של המצבים שאנחנו מתחלקים אליהם פה בסך הכל?
This is the 6 possible normal Fock state, non-mixed Fock state. Right? Okay. So, again, we want to find the eigenvalue and eigenstates of the system. We have 2 very simple ones, P1 and P2. You can see very clearly that an upstate cannot go into a position where there's already an upstate electron. It will cross a Pauli exclusion principle. And there's no lattice space with 2 electrons in it, so there's no in-lattice interaction. Right? So if we take HPI equal to 0, and that's one eigenvalue. Now, wait 1 second. We can, let me just notice that we can define a Fock state using our definition here, where we take each possibility in the lattice as a number, Fock number, and using the general definition of the Fock state, we can rewrite our vectors. So let's do it real quick. P1 equal to 1, 0, 1, 0. P2 equals 0, 1, 0, 1. S1 equals 1, 0, 0, 1. S2 equals 0, 1, 1, 0. D1 equals 1, 1, 0, 0. D2 equals 0, 0, 1, 1. Alright, so again, we have 2 of the eigenvectors. Anyone has any suggestion on how to find the other eigenvectors, eigenvalue, eigenstates? There's the classical method. Make a matrix, diagonalize it, and then find the states. Then in reverse find the states. Which is very comfortable here because we only have 6 different vectors, each of them divided to 4 components. So technically we just need to solve a 4x4 matrix, which is very, very simple. But what will happen if I want to add another lattice site, or another 2? If you have 4 lattice sites, notice that a 4x4 cubed matrix transformed into a 16x16 matrix. Not so nice to diagonalize. So even though this method is solvable in our usual way, I want to introduce a new method to solve this, to find the ground state. In this case,
רגע, למה אתה יודע שאלו מצבים העצמיים שלא יש פה 6?
This one?
כן.
Try to operate this state on a Hamiltonian matrix, and you'll see that the hopping term will give you something different than the S1.
רגע, אבל יש לך פה 6 מצבים, במטריצה שלך אמור להיות של 4 על 4, לא?
Yes.
אז איך יכול להיות שיש לך 6 מצבים עצמיים במטריצה שלך?
The 2 extra eigenstates will be some sort of cross terms.
הם לא יכולים להיות אייגנסטייטס השניים הנוספים, כלומר יש לך 4 ערכים עצמיים ל4 מצבים עצמיים.
You have 2 now. Well, you only have 2 now.
רגע, אבל יש
The
לך...
P1 and P2.
אוקיי, זאת אומרת, אתה יודע ששני אלו הם מצבים עצמיים... אבל רגע, מה המילטוניאן שלך?
Go back to the Hamiltonian and check it. You can check it yourself. I wrote the equation of the. All right. So, why is it so hot here? Okay. So. Okay. So instead we'll do a simple position that has these 5 steps. First of all, you will assume U much bigger than T, right? Because we made this assumption, we can take HT to be contributing to some perturbation term. Basically what step 2 says that conceptually we can say that the hopping term is very, very weak, and it only the ground and the eigenstate is only changed a little bit by it. It's mostly using the U terms, the in lattice interaction. All right. Then 3, we're gonna do some canonical. Canonical transformation. H goes to H type. Basically, I want step 3 is taking our conclusion from step 2 and trying to implement it effectively into the Hamiltonian without changing the physics. We'll see what it means in a second. 4, we want to project onto the SI subspace. Again, why can I do 4? Because we want to find the ground state, and the in lattice interaction will be very strong. We assume U is very, very big, so we'll assume that the ground state will be somewhere in the SI subspace. Basically, the subspace where you don't have the in lattice interaction. Okay.
שאתה מניח שאינטראקציות בין שניים הן יותר חזקות?
I assume that, okay, to find the ground state, you want to find the absolute lowest amount of energy, and if U is very, very strong, you can assume that any sort of state where you have U involved in it will be very, very high positive energy. If you go back to the Hamiltonian, you see that the U come with the positive sign and the T come with the negative sign.
אז אתה אומר שבגלל שכאילו U מאוד מאוד עצום, אז כאילו אוטומטית כל מצב אחר עם U יותר גבוה.
So I can assume that the ground state is the minimum energy eigenstate will be somewhere around the SI subspace. Right. The next, we write this state will be implemented by writing the transformation PS H tag PS, where PS H tag PS will PS is basically the projection operator into the SI space, subspace.
רגע, אבל גם ב-P1 ו-P2 יש לך ששניהם לא נמצאים באותו מקום, אז למה אתה לא הולך על P1 ו-P2?
We already know that this eigenstate with the value of 0, but I want to find an eigenstate with the eigenvalue of minus something. Wait. We know that these are not the eigens. These are not the ground state. This is some dark state.
Okay.
If we're talking about dark states, I'm gonna. Okay. If I already said dark state, I'm gonna give you a little bit of enrichment, something cool. If you take a 3-level system, for example, where your only interactions are going from level 1 to level 2 and from level 2 to level 3, I can transfer atom from level 1 to level 3 without ever going to level 2 using something called dark state with eigenvalue 0. We'll see it in a different course, maybe, if you take it. But it's a very cool interaction, and this state is very interesting, just not for me right now. It's real something, not for me. Okay, so I'm gonna. It's a problem. I was thinking to myself, why do I want to keep on the board? I'm gonna erase this one. All right. Okay, so these are my 5 steps. Let's start implementing them. before I let them down, I'm going to jump to step 5 and talk a little bit about the projection operators. Just so everything will be clear. So, subtitle on projection. Alright. So what will be the angle with the operator PS? We want this operator, if we'll get a vector S state, it will return an S state, it will project onto itself, and if it will encounter this state, it will return 0. Notice again we are ignoring these states because, well, you know the eigenvalue and we don't care. I don't care what happened. I'm not even going to look at them. All right. You can. Yeah. For example, PS of the mode 1, 0, 0, 1, which you will recognize as S1. You have to give us 1, 0, 0, 1. And PS of 1, 1, 0, 0 will be equal to 0. You can solve this with like basically just some basic intuition. You find PS will be equal to 1 divided by 2 sum over I and I minus 2. So basically, if we have, if let's say we take a D state, it will have in one of these I location 2, which will give here 0, and one side will be absolute 0, will be a 0 total number of electrons, will give here 0. So this will zero out for these states and return F states or S states. Let's do. I'm erasing this. Okay. Almost died. Thank you. All right. So let's just do one example in writing, just to hammer the point. This 1 equal to 1/2 sum over ni minus 2. Oops, sorry. You're right. Oh. This one is 2 minus ni. My bad. Almost. Equal to 1/2 and 1, 2 minus 1. 1, 0, 0, 1 plus n2, 2 minus n2, 1, 0, 0, 1. And we see this overall will be n1, and this overall will be n2. It will be 1/2. 1 times 2 minus 1, 1 plus 1 equals 1. 1, all right. 1. All right. So this is the S.
מה projection operators עושים עוד פעם?
Projection operator take, let's say you have some combination of S and D, they will just give you the S part of this combination. Imagine an operation that take a random vector and just give you one of its coordinates.
אוקיי, אז למה PS מחזיר לנו את אותו מצב בשלישי?
Well,
השלישי PS.
this one?
כן.
Yes. It's an S state, and you can see the time calculation. Okay. I also, in advance, would like to define the projection operator over the D space equal to 1/2 square root of ni minus 1. You can take the liberty to check this one yourself. I believe in you. You can do it. Of course, just to complete the definition. Right. Can I?
רגע, שנייה, אני מציג את השורה האחרונה. סבבה, סיימתי להציג.
Alright. So now we're finally ready to start this transformation. This amazing transformation. Remember the first two steps? The first two steps were fully in our mind. Again, first step, we assume t is very, very small. Second step, we assume ht gives us some perturbation changes. And now step 3, we jump straight ahead to step 3 to find the transformation. I'm going to take an operator. I'm going to choose almost randomly this operator, divided by u, ht, pd, minus pd, ht, ps. Right. Initially, this seems like a random operator to choose to symbolize a perturbation. But if you look at it a bit, slow down for a second, if I want to still writing. No, I'm just waiting for you to finish to read because I want to explain why I picked this operator.
Okay, finished.
Right. Initially, it seems like a kind of a random operator to take, but if you actually look at these two elements and see what they actually do, if you take some sort of random state and put it in, we'll take this entire part, we'll basically change it to the S state, to an S state, give us the energy of the transfer, T minus T, and then transform it into the D state. And exactly the opposite here. So we have some sort of operator that really represents the perturbation between the S state and D state. Basically, what the HT part of the Hamiltonian actually does. So logically, this is an operator that represents our perturbation, small changes between the states. All right. And the constant here, it's an arbitrary constant that you show in your homework fits really well with this following commutator. I love when I will have to do things and it's all in your homework. Alright. We pick this operator so that the following commutator will give us this result because we think ahead. Alright. And if you have problem understanding this operator, for example, for the basic verbal explanation that I gave, try to remember that PS in first quantization SI PD equals sum over bi di and ht b minus t sum over and you can check what I said in a much simpler way in a first quantization if you really want to do it by yourself. Check using this. It's a much simpler way to write it. And let's erase here and continue. Now I found the operator that give us the perturbation, and we're going to use the. Do we have a different marker? 1 second. Switch markers. Still bad. Bad to the bone. Green is good. Green is very good color. No, red is a good color maybe.
This color was good.
What? This one?
Yes.
I think it stopped working. Yeah, it's fine, but it's quick. Schreifer. Schreifer-Wolf transformation, which simply state if we have some small perturbation, we can create this following change, unitary change. This canonical transformation, that's more accurate. E to the minus. Notice this t is not time, it's RT.
זה מה שריטר?
Schreifer. Schreifer-Wolf. T.
טרנספורמציה קנונית.
This is a canonical transformation, yes. Right? This is, yeah. This is step 4. This is step 4 and 5 projection. This is just a transformation to the Hamiltonian. Doesn't change the physics, but assumes small perturbation.
רגע, אז אנחנו עשינו את השלבים 4 ו-5 וחזרנו ל-3, או שאתה רק מציין את השלבים?
We didn't do yet 4 and 5. We made some preparation for them. We didn't do them.
רשמנו את ה-perturbation terms.
This is just the beginning of step 3.
perturbation terms היו מה שעשינו לפני הדבר הזה של הפעולה?
No, this was the projection operator that we'll use later. You seen this equal sign what comes here? Development of this. If not, this is just a Taylor series of the multiplication of this operator. Notice that there can be an operator in an exponent. Absolutely legal. And it's a non-Taylor series, which you should remember for the future, because this is also how you advance Hamiltonian in time. Operator in time using some Hamiltonian. So this equation is very important. I will write it down. So, let's open it up. I would like to separate our H to HT and HU. So, H turns to HU plus HT. The first order commutator is minus T F H u minus t f ht plus t squared divided by 2 f h u. And I'm going to stop here because I'm only developing up to second order in t. Alright? Alright. I only want to order up to, sorry, I'm cutting my Taylor expansion in t squared. The reason I left this part in is because we know that this commutator will give us 1 divided by t squared. So it's still legal. Okay. So, using this commutation relation that you so bravely found by yourself in your homework, right? We know this term will transform to ht and cancel out with this one. All right. This term will, it's right here, be 1 divided by t ht. So on overall, this term will be t divided by 2 f ht. Okay. Overall, our change, our Hamiltonian will be hu minus t divided by 2 f, commutator of f and ht. I want to do the projection into the S subspace. Right? So we know that the S subspace has no contribution from the in lattice interaction from HU, so we can just ignore HU and just concentrate on this commutator part. So F ht would be equal to 1 divided by tu. I'm just opening it straight from the definition of f and ht. So ps ht pd ht minus pd ht ps ht minus ht ps ht pd plus ht pd ht ps. Right. Now I want to take the projection of this commutator, so we want to take ps of commutator f ht ps. We can use the fact that ps pd be equal to 0. So, since the two subspaces are orthogonal to one another, trying to project to one and then the other will be actually 0. Okay? So, plus using PS equals PS, projecting twice into the S space, will just give us again the S projection, and overall so this term cancel out. The first term will be 1 divided by UT PS HT PD HT PS, right? And we'll see that the second term will be exactly the same. So instead of 1 divided by UT, it's 2 divided by UT.
באדום יותר טוב.
Maybe. I can't believe I paid money for this one instead of just going to this section. Going and taking free markers. I feel so scammed.
אפרת לא נותנת לך.
Huh?
אפרת not give.
Let's see. I wanted to, spare no expense, and I got screwed over. I'm gonna erase this one. Okay. Now, again, using one of my favorite sentences in the English language, you'll show in your homework that I can't. It's amazing. It's amazing. PD HT. I can't believe it. Be equal to T squared 1 plus sum over sigma tag.
יש שם שתיים חלקו בביטוי שם? מה יש לך?
2 UT.
UT, רציתי שבכפלה ביטוי שם? זה U גדול ביטוי כזה.
UT. All right. Okay. So, basically, if you read this equation, it will give us some constant energy plus switching of 2 electrons. There's an electron on each side, and then just the energy of the switch. Okay. So, overall, you'll show in your homework that this will be equivalent to multiplication of 2 spin operators. Basically, we can write again. PS. Equal to J divided by 1/4 minus 4 plus 9 J. Well, J equals 40 squared divided by U. Square? Yeah. All right.
רגע, אז המעבר מהשורה השורה הבאה זה כאילו המעבר שאנחנו נעשה בשיעורי הבית?
Yeah, this and finishing the calculation of H tag, which I didn't write here, but it's I already erased the line Remember that here there's another times t outside the h tag. You can write it. All right. So we see here we still get some positive energy state, eigenstate. It has to be of a spin lattice, which you can probably identify it as an Ising model, which will give us an antifermionic relation, so an isolator. All right. This entire process can be expanded to an infinite lattice simply by the expansion the expansion will use exactly the same process. It will just give us divided by u. The absolutely general, most general Ising model. So we started from lattice with hopping and in location the energy, and found the general Ising model. Which makes sense. I mean, Ising model is just what we did here. It's just some electrons to spin around. Except that here the spin around is by switching between the electrons, and in the Ising model they just switch the direction of the spin. But but it's practically the same. I mean, if you just for a thought experiment, if you change these two locations up, these two operators up, you just see that you have an Hamiltonian operator here that describes spin flips. Yeah, it's very logical that we concluded with the Ising model. What? This no. Alright. Technically you don't have to assume nearest neighbors here. It will also work more generally if we remove this. It's also fine. I just wanted to make the assumption of you can just jump one lattice space. But if you don't jump just one lattice space, it will be like this. You get the same result.
אז אנחנו שזה אמור להיות בין כביכול אחד פה, מכיוון שאנחנו שיש את הכאלה הזה עם הפונקציות האלו של
Oh no, in our case we have just two lattice space. You can't jump two locations. You only have two.
בגלל זה אותו דבר. בגלל זה אותו דבר בעצם.
Notice that the Ising model can also go up to higher orders of interactions.
Yeah.
So, and we can, and if you want to do this exact same calculation, but like 17 pages long, you can prove this equation. But don't worry, this is not in your homework. That's a positive. Okay, any question about this model before we go to the very useful weak theorem?
איפה בדיוק עשינו שלבים 4 ו-5 של התכלס אחסון?
We did. We didn't. Okay, technically we didn't finish by finding all the eigenstates, but there's two little caveats here. First of all, we did it here like sort of a hand wavy style, instead of just straight calculation. You can look. You can see that this. You can try to find out what the matrix that give this operator generates. You'll see that it's a very simple matrix to solve, very trivial matrix to solve. And secondly, a note about this entire method. Look that we achieved some sort of approximation for the ground state, but we completely lost all the data for the excited state. So it's not a perfect overall solution. It's some approximation of a solution to find a specific case that we're looking at, usually in physics, ground state. Specifically in this case. So yeah, we did lose some information. That's a asterisk that needs to be said about this entire process. So, can I erase the board? Can I? Yeah, all right.
מה היה החיסרון הראשון עוד פעם?
The first, did I say two?
אמרתי שיהיו שני דברים, והשני היה שחסר לך מידע על דברים אחרים בעקבות התהליך הזה, ואז היה עוד חיסרון נוסף שהבאת.
Oh no, I forgot. Let's see if it's written here somewhere. I don't think there's another one. Did I say two?
אמרת שני דברים.
No, there's only one written here. Only one reason. Only one drawback. All right. What's the time?
7.
7. All right, that's good. That's good. It's good.
7 to 7.
7 minutes to 7. Yeah, we might finish early, a little bit. Not so much. All right. So, week 3. What we want to do now is explore the weak theorem, which will basically give us another calculatory, I think that's the word, another tool to simplify a calculation. Basically, if you have, for example, you have a ground state and you want to enact some long list of operators, instead of doing it manually, you can use weak theorem to get a quicker result, depending on how fast you're using it. Alright, so before we talk about the theorem itself and prove it, we have to make some basic definition that you already saw in class, so I'll go over them really quick. First of all, we're only going to talk about the bosonic case. Efrat already told you the difference. I just don't want to follow the -1 all the way, so just imagine that we're only doing this for bosonic, that's it. Because. First of all, we want to find the normal order. Normal order of, let's take for example, A, B, C, D, alright? This notation basically says, take those 4 operators, A, B, C, D, put all the creation operators to the left, all the annihilation operators to the right. This is not an operation on operators. This is just some notation. For example, N, NK, AL dagger, AN dagger, AN equal defined as AL dagger, AN dagger, K. Okay. So let's see how we can actually take this string of operators and find the normal order and like get in an equation the normal order. AL, AM, AN. Right? So to achieve the normal order, I want to push these 2 operators back and this one forward. I'll start by switching these 2 around. Right? So to switch them around, we have to first of all add a commutator, AK, AL. Only bosons today in today's class. We do not respect fermions. Right? Plus switched. I'm pretty sure you'll have one in your homework. Oh, my favorite thing. I want. If we have time in the end, we'll show it. I'll show it. Or you can come to me in the end. Again, doing this the exact same thing, replacing these two operators. We all know the deal. Plus AL bugger K and bugger N plus M bugger N bugger K N. Notice that I'm going to stop right here because this is normal order already. This is normal order, all of our different elements of the models. And this here, the final one here, this will be N of AK, AL dagger, M dagger, A, what did I say? N. Okay. Next, we will want to define the contraction, called contraction. Contraction AB equal to AB minus normal order AB. This will give us two possible situations. If A and B are already normal order of AB is just AB, it will be 0. If A and B are not normal ordered, this will just be BA, and this will be just a commutator of AB. If AB not normal order. Okay, so we can rewrite our equation right here. K AL AM AN will be equal to N K AL dagger AM dagger AN plus K AL dagger contraction AM dagger and plus AL dagger AK AN dagger AN contraction here. Yeah. Now, when we write contractions, the two elements don't actually have to be next to each other. This is the same as writing AK AL dagger AM dagger AN. And lastly, notice that this is the remaining operators here are in normal order, and also here are in normal order. So I can take this normal order sign, just expand it all the way outside, all the way to the end. All right? All right. All right. Let's take, for example, the first one. Okay? This contraction is a commutator. The commutator of creation or annihilation operator will, by definition, be a number, either 1 or 0, right? And those two, the following operators, are already in normal order. The creation is on the left, the annihilation is on the right. So, putting the notation normal order on this this set of operators will change nothing. So I can put them inside the normal order notation that I already wrote. So this, and eventually writing it like so. Okay?
אבל הפרטיס, זה רק על זוג איברים, לא על שלושה זוגות, נכון?
What? Oh, the contraction here, it's just on these two.
אוקיי.
It's just on where the bridge shows.
זה תמיד
Makes sense.
על זום.
Only on two. Yep.
ואז כל היתר פשוט, כאילו אתה מעביר את המספר הצידה ואת כל היתר אתה משאיר כמו שהם בסדר הזה. נכון?
I'm not sure exactly what you said, but
Just-
מה שאמרת לגבי הקונטרקשן ששווה לקונטרקשן אחר.
you want me to
בעצם-
stand there or there?
כשאמרת שהקונטרקטור לא חייב להיות שני איברים סמוכים, אז כאילו מה שאתה אומר, אתה עושה את הקונטרקטור, מוציא אותם החוצה ואת כל היתר אתה משאיר.
I just wanted to say that the contraction is only the notation. And and moving the notation a little bit around doesn't change anything. It will help in future. In the
כאילו אתה
future.
אומר שכאילו
Near
A
future.
K A M פלוס כאילו עובר לצד, כאילו כקונטרקשן, ו-A פלוס ו-A N נשארים לצד.
I'm just keeping this in the original order. That's all I want to do. Just keeping the original set of operation. The order of the set of operation. So here's the statement of the theorem. If we have, let's take for example, four operator, just to make a simple example with explanation, A, B, C, D, and we'll write the normal order operator that equals this equation. It will obviously have the original operation, plus it will have every possible contraction. So I'll just write them down. This is going to be long, but I'm not going to do it once, so it's cool. So it's okay. AB contraction CD plus A, B, C, A contracting with C, D, plus A, B, C, D, A contracting with D, plus A, B, C, D, B contraction with C, B contraction with C, plus A, B, C, D, B contracting with D, plus A, B, C, D, C contracting with D, plus I'm going to write this one in the another line, A contracting with B and C contracting with D, plus A, B, C, D, A contracting with C, B contracting with D, plus A, B, C, D, A contracting with D, B contracting with C. You can check me on this. This is the most general equation to find the normal order, the equivalent normal order operator. Alright. So the first step of Weak theorem is that Weak states that this sort of development can be done to any number of operators. We'll prove everything after we finish talking about Weak theorem. Right? So Weak state that this is available for every set of operator, no matter how many or what operators you have. Second, the expectation value of this set of operation, if it's like that, expectation value with vacuum on the other side will be equal to the sum over the what we call fully contracted operators. Basically, all the operators that have only commutation relation, which makes sense, right? If we have some sort of operator that still has active operators in it, let's say for example BC, and it's in the normal order notation, the annihilation operation will be on the right and the creation operation will be on the left. And we know that A0 equal to 0 and 0 A dagger also equal to 0. So all these terms will cancel out the expectation value and only be left with the fully contracted terms. Right? Yes. So if we'll take our example, I'm gonna write it write the full case, just go over everything. So I'm going to write all the possible contraction, even the one that will obviously zero out. I'm not gonna write the heads. Who's got the time? Okay. This plus another. No, it's very loud, I'm sorry. Okay, let's go over them one by one. Nothing going on here. This is legal, it's not normal order. This one is again not normal order, but notice that it will be either one of those, either this or this from the delta from the commutator, right? Because right, so it will be either this one or this one. Okay. Then this one is also this one will also cancel out from this one will zero out because this is two annihilation operator, again two creation operator. AL dagger AM is normal order, AM AN is legal. Right here we have non-normal order commutation contraction, which is legal, and then a normal order which will be equal 0, so this one will cancel out. Again, here we have a normal order one, and those two are normal order by being annihilation or creation. So I get this one. So while we did get an extra term, it will cancel out due to it being either aka M dagger or aka L dagger by the delta. So we got all the way back to this result. Up to changing the M.
שני גורמים האחרונים נפסלו מכיוון שהם פשוט בסדר.
I forgot. I don't know.
שני הגורמים האחרונים נפסלו מכיוון שאחד מהסמלים ביניהם היה בגלל שהם פשוט היו מינוסים אחד של השני והימין נפסל מסיבה אחרת. למה שני השורה האחרונה נפסלה?
This one?
כן.
Look for AL dagger AM, normal order, and AKAN is also
זה שני גורמים אמרנו, fully contracted.
Fully contracted. Those three terms are fully contracted, but they all can't zero out because they all have some normal order contraction.
כאילו אתה מתכוון שזה צריך להיות בגלל מה שאמרנו שהם הדלתה, נכון? פונקציה דלתה.
No. The delta is something else. What we use here is AM, AK equals 0 equals AM dagger, AK dagger. This is the final. And here it's because those two are normal order going back to here. That's it. Okay. So finally the application of Weak theorem states that if we have for a set of operators, for example, A, B, C, and D, this will be equal to sum over fully contracted term. So in our example, without even writing, we see that to the left we know fully contracted term, that this example will be 0. Right, let's prove this. Proof of the theorem.
רגע, שנייה, שאני יכול לראות פה כזה רגע?
נתחיל, stop there. When I erase the entire board for the proof, so act quick. Can I? So, let's start the proof by defining a general case. We'll call it omega n. And omega n will just be A, B, up to some operators. Overall, this has n operators. In short, omega n symbolizes a general state with n operators in it. And we'll solve this by induction. Basically stating that we start with 2 operators, show that it works with 2 operators. Sorry. And then we'll assume it works for n-1 operators and see that it also works for omega equals n operators. Right? So, first step, omega 2 equals AB. Okay? We know AB is equal to, we can very simply show AB equal to AB minus AB contraction by plus here, sorry, plus. By definition.
No.
It's the light.
It's the light. There's some things I can't control. Some things I'm going to ignore it. Right? This is again. We want to just to reiterate. We want to prove that there is a notation. This notation that we can use it for any number of operators. That's the main body of operators. Okay. So now step 2. Assume the theorem works for omega n-1. Okay? Now we'll create. It's just trivial. This is a commutator, and it's just by definition of commutation. Yep. All right. Okay, so now we want to generate another operator, omega n, to be equal to A times B Z. And specifically, we're going to choose the term B through Z to be equal to omega n minus 1. Again, because those omega represent a general ensemble of operators, we can do this distinction. We can just create another operator, the next n, by just adding 1 operator instead of generating a completely new set of operators. Okay? So, what can we say about this omega n? We know that we can represent this n-1 state as some normal order of states. So it will be A times n of B to Z plus what we will call all contracted contractions. Alright? So far I did nothing. I just open omega n minus 1 by what the theorem told me I can do. Okay? So, we can open this n definition up again just to organize our equation. A equals n b to z plus a times n all contractions.
What is it, contraction?
You remember when we had the four operators and we did all the possibilities of the connection? Yeah,
Yes.
this is all the contraction. Not to be confused with fully contracted. This is all possible contraction. 1, 2, 3, 4, whatever.
יש לנו את כל האופציות של הקונטרקשן שרק קונטרקשן אחד, עם כל האופציות שיש לנו שתי קונטרקשורים.
And so on and so on. This is every possible contraction. We know that we have every possible contraction for n minus 1 from the assumption of the recursion. Right? So, now we encounter two states. Either A is a creation operator, and then we're done. It's already in normal order. Okay? Or B, A is an annihilation operator. And what I want to do if A is an annihilation operator is just push it all the way to the right. Okay? So, let's start from this element. To push it, I'm just going to use the commutator. B to Z. This one equals to. I don't know if you remember from your homework, from your previous homework. There's an equation for multiplication in the set of operators. Equation for contractions. Go to AB, commutation C, Z plus B, A, C, D, Z plus B, Y, A, Z. Okay. So, we see here, if we replace this commutation relation with contraction, you basically see that this equation will be every one contraction. Every operator in the, I'm just going to write it to make it simpler, instead of just bumbling around. So be equal to n of A, B, Z plus A, B, C, Z. It's all the first order contraction with A. Let's start with A. Okay. And notice and we'll get that A, B, Z, Z equals normal order B, Z times A plus A, B, Z. Okay. Next, we'll also want to switch this A to the other side. Again, we assume it's an annihilation equation. The A that multiplies all the contractions the other side. So again, we'll have n all contractions A plus A and B Z. Okay. Sorry.
לא רואה את ה...
Just gonna erase this and write it again below.
זה שחור,
A sick and all contractions. Now we came to a really interesting case.
It's plus, yeah.
You want another one? You want another one? All right. Okay, not the final boss. I'm just kidding around. Okay. So what do we have here? Let's go over our 4 different elements. When you're ready. When you're ready, go. You can.
What?
You want to take a picture?
Ah.
So before I go back there, and there you have your picture. All right, so let's go. Let's review our entire set of operators. This one right here. This one right here is the normal order of the original state. This one right here, we shown here that this is just the contraction, the single contraction with A. Okay. This one is every contraction that doesn't include A, as we see here. And similarly to how we approach this part of this term in the equation, we can get the exact same approach using the last one, and we see this is all the contraction that don't involve A, including contraction of A. So we have all possible contractions here.
איך אתה יודע אבל שזה בשביל 4 האיברים שנקבל?
I know. This is
נראה
the
אתה
form.
שיבת את כל 4.
I take this equation. Again, I'm gonna do the final step verbally, very simply. If A is creation operation, we're done. Right? This is already normal. If it's an annihilation operation, we want to take it to the right here and to the right here. Okay? How do we do this? How do you do this? Commutation relation. Right? Okay. So we move A to the side and create commutator here. And again, for all the other contraction, we move A to the side and add the commutation part. Okay. We already showed that this term will give us all the signal contraction with A, right? This one will give us all the contraction without A. This one will give us all the contractions, including another contraction with A. And overall, we have every possible contraction like that.
אז פלוס כל האחרון שמיותר, נכון?
Yeah, it was a joke.
עכשיו הדבר שני...
You got him.
אוקיי, רגע. לגבי החלק של רציתי לעשות פה יחס קומוטציה. למעלה, בשורה...
You mean this one?
כן, לעשות פה יחס קומוטציה. אז עוד פעם, כאילו, פתחת את כל הדבר הזה שכאן, נכון?
There's a bracket missing. Oh my goodness. Right.
אז אני אעשה פשוט מבולבל איך עושים את המעבר מהשורה הראשונה הזו כאן.
From this to this way?
כן, אני קצת מרגיש מבולבל.
This is a known relation.
אוקיי, לא, זה אוקיי.
Commutation of one operator times a set of operator will be a sum over single commutation, all the possible single commutation.
אוקיי, ואז כאילו פתחת את זה פה בפנים בשורה השנייה, בשווה...
This one, just one identity.
אז כאילו רק פתחת את זה בצורה מסודרת ורשמת את זה פה. ואז המשכת מזה לחלק האחרון, החלק האחרון.
Last part?
רק איך הגעת לכאן, כן.
Oh, this one just... Here. Switch those.
כדי להעביר אותו פשוט אחרונית, אז פשוט עושה החלפה בין השניים.
And just by definition of how we swap operators in commutation relation.
לא הבנתי, זה מגיע מכאן או שזה דומה?
It's equal. It's the same. Notice.
Yeah.
A to Z, A to Z.
אבל זה לא קשור אחד לשני.
I wrote this again just so we'll have the entire picture and it will be much easier to explain. Where all the elements are. Again, the set of operator itself, commutation with A, one commutation with A, all commutation that don't include A, all commutation that are more than one set of commutation with A, which will of course include everything. All the set, all the elements that we have in the original weak theorem. This is the solution. This is the proof of the weak theorem. Again, we state that the weak theorem is also the expectation value part, but actually the weak theorem is just this. In the expectation value method, it's just something that we derive from weak theorem, because it's very simple to see that only the fully contracted states matter. So, what will be the expectation value of 5 operators?
Okay, אלה שהם fully contracted.
Okay, that's the next step.
Okay, so בוא נראה את זה.
0. You can't have fully contracted because
אתה צודק.
contraction has to be
מספר זוגי שלם, מספר שווה של הורדה ושל יצירת סכום.
That's also another point, yes. Alright, you can, yeah. So in your homework, I'm just going to give you a little spoiler. I wrote a question with a huge set of operators. You just have to think of it logically, solve it quickly. If not, you can try to do it by hand and like, I don't know, take like 2 hours to add this square root of 2 or divide the square root of 2, add square root of 1.
צריך יהיה לתכנת?
No. I'm just saying there's going to be a question with many different set of operator that you have to find the expectation value using smart method instead of just doing it by hand, which mean logic and weak theory. That's about it. Hope you enjoyed today's class. The next class will be in 3 weeks. It means that you both get shorter homework because it's going to be the second half of the usual homework of the application of second quantization, because we couldn't do everything in one class, so you get like half the homework.
Why 3 weeks?
And 3 weeks because I won't be here 2 weeks from now, so I switched with Efrat. So we'll have another lesson in 3 weeks, and then another one in 4 weeks. I mean, a week after the next lesson. And I still don't know. I still haven't shown what will be the state of the homework, considering you have 2 consecutive weeks. You might just get 2 small set of homeworks together, one after the other. I don't know. We'll see. Enjoy. Next class is BCS theory, which is awesome. I love BCS. It's probably like my second favorite subject in this class. It's very hard. So, couple of them.
קודם כל לגבי הגורמים האלו פה שמצאת אותם עוד פעם, אני קצת עדיין מרגיש